group of Year 5 students from Daman High School, and we are presenting to you on Introduction to Artificial Intelligence, Machine Learning with Python. Okay, so here is an overview of the module today. So first, I will be going through artificial intelligence with a brief introduction to AI and the loss function. And then after that, I will be talking about regression, which is a method in machine learning, and that is about fitting data to a point and predicting future data points. And then after that, Ting will be taking over, and he will be talking about Perceptron Learning, where he'll be using Perceptron Learning for classification. And after that, Ian will be talking about SVN, which stands for Support Vector Machine. That is a versatile method in both classification and regression. And afterwards, Ian will be going through, will be consolidating your learnings today. So without further ado, let us go to, feel free to drop any questions that you may have in the Zoom or Discord chat. Thank you. And okay, so without further ado, we can start on introduction to AI and classification as well as loss function. So firstly, what is classification? Classification is really about a supervised learning task of learning a function that maps an input point to a discrete category. So examples of it, like using data such as humidity and pressure to determine if it's going to rain today. And of course, you can also use other data such as like the duration that the sun is on, and also using using past emails to determine if an email is spam or not, and like classifying dogs and cats. Yeah. So yeah, here we have some diagrams to illustrate the concept of classification. So over here on the right, we have two different types of data points. One is the blue circle, and now is the green triangle. So we report these data points according to their x and y variables. Like for example, in this case, say x, y could be like humidity, x could be like pressure. Then for example, for this given blue circle here, with this particular value of humidity and this particular of pressure, perhaps maybe it rained on that day. Like some human will collect a data of past humidity and past pressure and see if it rained on that day. So maybe for this particular day, with this particular pressure, this particular humidity, this particular pressure, and it did rain on that day. And for like the triangular point, it could be like with this particular pressure, this particular humidity, then it did not rain. Then after plotting these data points in the two-dimensional graph, then you can draw one line that cleanly separates these two classes. And then after that, if we have another data point, say with this pressure and this humidity, then you can classify it because it's on the left side of the line. And therefore, it should most probably be class A, which in this case is that it will rain, like the other blue circular points. And another classification task is like classifying whether an email is a spam or is it not a spam. Okay. Yeah, so yeah, for example, using past data for like past email, some people may go classify if it's a spam and if it's not a spam. Then using perhaps like the words that is contained in the email, then the machine learning algorithm can try to predict if a new email is spam or is it not a spam. So okay, so yeah, when it comes to machine learning, ML, there are like some ultimate difficulties. And so firstly, we want to know what kind of model to use because there are really many different models out there, and we need to know which one we should be using. And to understand what kind of model we should use, we need to know what is the purpose, which determines how efficient the model has to be. And this here comes our ultimate difficulty. What kind of data do you need to collect? And also what kind of parameters do you need to have, and which will be covered by 18. And okay, so let's imagine. So we have a problem here. It's like how much I can get for my upcoming essay that's say on like econs, and if I don't study. So perhaps you have like some inputs which could include like number of hours that I study, which certainly is a really important factor in determining how well I would fare in that paper. And also another factor could be like number of revision questions that I do, as well as the difficulty of these revision questions, and of course number of tutorials that I actually listen in class, which may not be that high, and also the hours of sleep per night, and also other commitments like building blocks and some other projects that I spend quite a lot of hours on. Okay, so now we have, so we'll be focusing on this. What kind of data we will collect and how to collect data and what is the purpose of that data and whether the data is accurate or reliable. So, okay, for like accuracy. Okay, so let's say like you ask this question, like how much do you like to eat? It's very likely that people will reply a lot because I think many people like to eat, if not all or most, yeah. So the distribution of responses will actually be left skewed, what we call left skewed, which is like as shown as illustrated in this diagram, where like it's not where the peak is not at like the middle, but is skewed towards the right in this case. Yeah. And this makes it harder to identify the features of this distribution. And so in machine learning, it's important to ensure that the distribution will not be skewed. In other words, it's like a normal distribution in which the peak is like at the middle. Okay, so how can you do that? So if you cannot collect a best data, you can just transform the data. There's some big brain code. Okay, so now I would like to introduce the concept of standard scalar, which is a function that transforms a distribution into another distribution whose mean value is 0 and standard deviation is 1. And the data is transformed to this case. And so what do I mean by standard deviation? So standard deviation is given by this complicated formula, which I think is taught in secondary 4, but it's okay. Okay, just explain this formula. So suppose that you have a set of data and you call that xi, where I could, like, for example, if you had 10 data points, like each one of these x1, x2, x3, x4, x5 until x10. And then xi, the I here is just any number from like 1 to 10 in this particular case. And then this weird-looking alphabet called mu is actually the average, or the mean of the data points. So the average of that 10 data points that we have. And then this n is just the total number of data points we have, which is like 10 in this case. And standard deviation is just the summation. This is a sigma notation, which I think Eating will be elaborating later. Eating will be elaborating later. And sorry for the disruption just now. And okay, so like what standard deviation is, it's really about summing the square of the difference between a data point and the mean of the distribution. Then you square it and you sum it across all the data points that you have. And then you divide it by the total number of data points that you have. Then eventually you take a square root. So that in fact this because so that the standard deviation will have same dimension, same unit as the value as the data point that you have collected. Yeah. Okay, so yeah, this may sound complicated, but let's look at some graphs. So here we have this more sharp graph, more like taller graph, I would say. And what this graph represents is that it has a small standard deviation. So what this means is that a small standard deviation means the data points are closer to each other. And in this case, you can see it's like compressed to a middle. And that's why the data points are really close to each other. Like they're very close to the mean, sorry, yeah. And then for like the distribution with a large standard deviation, which like the fatter one at the bottom, like this one here. And you can see it's really, the data points are really distributed further away from the mean. And yes, and in this case, you can see that like going back to this standard scale. So a standard deviation of 1 means that like it's really relatively close to the mean of the distribution. And so now we are ready to go on to the next concept, loss function. So there are many different types of loss function, which includes like 0-1 loss function, L1 loss function, L2 loss function, and for classification problems, we also have hinge loss as well as cross entropy loss. But for this workshop, we will be only going through 0-1 loss function and L1 and L2 loss functions. Yeah. Okay, so for 0-1 loss function, we can let L of actual and predicted denote the loss function. And for 0-1 loss function, the value is like for a particular data point, then if the machine learning algorithm predicts that let's say, for example, today, if the machine learning algorithm using the pressure estimate of today, it predicts that today will rain, for example, but actually it did not rain, then the L1 loss function, the 0-1 loss function, sorry, the 0-1 loss function will return a value of 1 because the actual value is not equal to predicted value. However, if the machine learning algorithm predicts that it will not rain today, and indeed it did not rain today, then the 0-1 loss function will return a value of 0. So in this case, you can see like if the machine learning algorithm is wrong for this particular data point, then L0-1 loss function gives a value of 1. And if it's correct, then it gives a value of 0. And one thing to note that is that for 0-1 loss function, this is only for binary classification, which is like an absolute classification, in which the algorithm outputs either yes or no, and not like a probability. Like for example, if the machine learning algorithm uses a probability, gives outputs a probability that like 0.7 probability that it will rain today, then you cannot use 0-1 loss function. because you don't know what is the actual and predicted value. Yeah. And we can see that in the L1 and L2 loss function. Okay, so yeah, to further illustrate L1 loss function, we can see this distribution here. So let's say we plot the pressure against humidity point, humidity values, and let's say the red values, the red circles are points, days in which, like, with this particular pressure and this particular humidity, and it did not rain on that particular day, that is classified as red here. And for blue, it could be like with this particular pressure and this particular humidity, it did rain on that particular day when we went to collect a data. So after you have plotted all these points, all these data that we have collected earlier, and you can see that you can actually draw a line to separate quite nicely separate the two colors. And in this case, let's say like we'll class and let's talk about Z1 loss function then. Okay, so if in this case you can see like generally because like most of the majority of the red data points are on the left side of the line, and so I think it's really reasonable to assume that given any new data points that, for example, is here with this particular humidity and this particular pressure, we will classify it as a red point, right? Like the machine learning algorithm will predict that given this particular humidity and this particular pressure, it will predict that in this given day, it will not rain, as like according to this line, this separation line here. And so like you can use this to predict future data points. And let's talk about the Z1 loss function for this particular distribution. So for like this red data point here, because on the actual day, it did not rain. That's why it's labeled as red. And using the machine learning algorithm, if you were to feed this data into your machine learning algorithm, the output will be it will not rain because it's on the left side of this line here. And as I said earlier, because the majority of red point is on the left side, so the machine learning algorithm will classify it as will not rain. So in this case, actual equal predicted. The algorithm is accurate in predicting whether it did rain that day. And so the loss function will give a value of 0 because it's accurate. But however, for this particular data point, this blue one here, on that particular day, it did rain. That's why it's blue in color. And so with this, however, with this humidity value and this pressure value, if you were to feed these values into the machine learning algorithm, the algorithm will output that it will not rain because it's on the left side of this line here. So in this case, the actual does not equal predicted. And because of that, like your prediction is wrong. So the loss function will give a value of 1. And the same goes for this red data point here. On the actual day, it did not rain. But because of its pressure and humidity value, and the fact that it's on the right side of this line here, the machine learning algorithm will classify as it will rain. So in that case, your prediction is wrong, and that like you predicted that it will rain, but actually it did not rain. So yeah, the L1 loss function return a value of 1. But for all these blue data points here, because they are on the right side of the line, and it did rain on these particular days, and so the Z1 loss function for these data points will be 0 because the prediction is accurate. And next up we have L1 loss function. So for L1 loss function, how to compute L1 loss function is such that like it's the absolute value between the actual value and the predicted value. So one thing to note that this for an algorithm, like the L1 loss function is used for an algorithm that outputs a real number, and it's not like a binary classification that has only 2 possible outputs, like whether it will rain or not, whether it's a cat or dog. Yeah. So like to better illustrate this, you can see like, yeah, you can see this diagram here. Like given a particular humidity and pressure value, the machine learning algorithm will output a probability, a real number that's between 0 and 1 inclusive. And yes, you can see for this like this L1 loss function here. And because L1 loss function, remember, is the magnitude is the absolute value between the actual value and the predicted value. So you can refer to this graph here. And what because L1 loss function is the difference between the actual value and predicted value. So like in this case, this blue point is the data that we have collected. So with this amount of money spent on advertising, this amount of sales induced by the advertisements, and this is the actual data point. But because of the best fit line is a method called regression, which I will be covering later, your machine learning algorithm predicts that with this particular amount of advertisement, you'll make this amount of sales. But actually you make this. So the L1 loss function is actually the distance, the vertical distance between the blue points in the line, and similar for all the other blue points. The L1 loss function for the data point will be the distance between a vertical distance, the L1 loss function for these blue data points will be the vertical distance between the points and the line. And next up we have L2 loss function. So L2 loss function is really similar to L1 loss function in that it involves the difference between the actual value and the predicted value. However, in this case, you need to square this difference. Yeah, like actual minus predicted square. Yeah. However, you need to note that, like similar to L1 loss function, this is an algorithm. This is used for an algorithm which outputs a real number. And usually in machine learning, we prefer L2 loss function to L1 loss function because it penalizes worse prediction more. Like a really inaccurate prediction will have a larger value under L2 than L1, since L2 involves squaring, provided a number is greater than 1. Yeah. However, if there's an outlier, that L2 loss function may not actually be representative of the overall performance of the algorithm. And in that particular case, we can either remove the outlier from the data sets or we just use L1 loss function. So to better illustrate L2 loss function, we can refer back to this diagram here. Like this, in this diagram, we plot the amount of sales induced after advertising and the amount of money spent on advertisement. So for example, for this data point, you could spend like $1,000 on advertisement, and then actually you induce like $5,000 from sales. But and the difference is 4,000, right? But because your machine learning algorithm predicts that perhaps you only induce $2,000, so the difference between the actual value and the predicted value is $5,000, the actual sales induced, minus $2,000, the predicted sales induced, and that's case is 3,000. And because L2 loss function involves squaring, so our L1 loss function return a value of 3,000, that is the absolute difference. L2 loss function will actually return 3,000 squared, which like I think is 9 times 10 to the power of 6. Yeah, it's a really big value. So in that case, you can see how L2 loss function really penalizes worse prediction more. So now, okay, so now we have come to another concept called overfitting. So overfitting is a phenomenon that occurs when a model fits too closely to a particular data set and fails to generalize to future data. So in that case, you probably get a very high training accuracy, or even 100%, perhaps, but a super low test accuracy. So overfitting occurs when you try too hard to minimize the loss function. So in this case, I prepared 3 diagrams here. And in the first diagram, it's called underfitting, in which you can see like from this particular distribution of the data points, you can see that a linear line probably does not really approximate the relationship between the output variable and the predictor variable well. Like that's in the case of optimal, the middle diagram, because you can see that the data points generally follow a curve shape as given by the optimal diagram in the middle. However, so by putting it by underfitting it with a linear line, you are actually like your accuracy will be really low because you cannot generalize to future data set because it's not following the trend of the data. And for overfitting, it really occurs with try too hard to minimize the loss function. So you try to fit such that, like for example, for L1 loss function, you try to fit such that all your prediction will be equal to the actual value. So in that case, you just get a line that passes through all the data points in whatever pattern. And in this case, you can see that it probably will not perform so well in the future. Because for example, given this data point here, which originally will have fall on the optimal case, like it will fall on the line. But because of overfitting, the data point is here, but the overfitting line will probably extend to here. So with this predictor variable, it's likely that the output variable will be very different. And in that case, your test accuracy will be really low because of overfitting. So now we have come to a general ML problem. ML stands for machine learning, yes. And yeah, so the general ML problem is called the bias variance problem, which the conflict in trying to simultaneously minimize these 2 sources of error that prevent supervised learning algorithm from generalizing beyond their data sets. So variance is really about generalizing, which is like underfitting, and bias is like overcorrecting, like overfitting. And in machine learning, it's important that we balance bias and variance. So we want an optimal algorithm that neither underfits nor overfits, which is a really hard thing to be honest. And so yes, sorry, give me a yeah. So yeah, we have this diagram here, which is a really good fit. As you can see, like it neatly separates the red points from the blue points. Yeah. However, what an overfitting algorithm is like this, in which you try too hard to minimize the loss function, such that in like here, using this line here, your training accuracy will be 100% because you can classify all these training data points correctly. Yeah, like the red point would be days that it did not rain, and blue points will be days that it did rain. And using this training data set, you have 100% accuracy. However, in the testing data sets, let's suppose that we have one point that's here, like with this particular humidity and this particular pressure. So in that in the optimal algorithm case, it will be classified as blue, i.e. it will rain on that particular day because it's on the right-hand side of this line here. However, under this overfitting algorithm here, because the data point is here, it's actually on the left-hand side of this line here, this boundary here. And therefore, as a result, it will be classified as it will not rain because it's on the left-hand side. So yeah. And another example is like this sales against advertising graph. And you can see that the points generally follow a linear relationship. So perhaps an optimal machine learning algorithm should be about a linear line here. However, what an overfitting algorithm is like this case here, in which you try too hard to minimize the loss function. So in this case, where you have all the training data set correct, like your training accuracy is 100%, your testing accuracy will probably be very low. Because for example, you could spend this amount of advertisement, which a lot, and by the linear relationship, which is probably the optimal and more accurate relationship, it should be somewhere around here. The sales should be very huge. But under this overfitting algorithm here, with this particular advertising, then if you were to extend the line here, you'll probably be predicted to induce only this amount of sales, which is very, very different from the actual amount of sales that should be induced. In that case, yeah, so your testing accuracy will actually be very low, even though you have 100% training accuracy. So yes, here are some memes for you all about overfitting. Okay, so yeah, and you can see from these memes here, it's like really about how bad overfitting is, in that your model cannot really predict new data, like this Pokemon meme here. And yeah, this meme here illustrates how overfitting is about like minimizing the loss function such that you fit all the data points nicely. So yes, I will give you all some time to digest here. If you have any question, you can just either text in the chat or Zoom chat or in the Discord. And remember to ping us. Yeah, thank you. Okay, so now we'll be going on to the more important content on how to avoid overfitting, which is really an important concept in machine learning, because we certainly do not want to have an algorithm that is overfitted. Yeah, because it will compromise on our testing accuracy. So in this workshop, we'll introduce 3 methods. So method 1 is regularization, which is a method that penalizes hypotheses that are more complex to favor simpler and more general hypotheses. So in this case, we can define a cost function, cost bracket H. The H stands for hypothesis. That is like the algorithm that you are using. Like in the case of the sales and advertisement graph, it could be the equation of the graph, for example. So the cost function could be like defined to be like the sum of the loss function, whatever loss function you adopt, be it 0, 1, L1, or L2, plus lambda times complexity of the hypothesis. So in this case, lambda is a constant that is set by you. And it's up to you how you want to set this value of lambda. So for example, if you want to favor a really simple algorithm, then you should probably give lambda a really high value. Because in that case, if the complexity increases by only a bit, because lambda is really big, you can see a really big value multiplied by a small value, it will probably still be quite big. So in that case, it pushes up your cost function by a lot. In that case, it tells you that you probably should not be choosing this complex algorithm. And in that case, you should more probably choose a simpler algorithm that even though may have a higher loss function, but it's less complex, as given by like a larger loss function value and a lower complexity value. And yes, so to illustrate this, let's consider a cost function where lambda equal to 10. So in this case, let's suppose that the loss function, whatever loss function that we adopt, has a value of 100. So, and in this case, because it's a linear graph, let's suppose the complexity value of this linear graph is 1. And our cost function, being loss function plus lambda times complexity, is equal to 100, the loss function, plus 10, the lambda value here, times 1, the complexity function, which equal to 110, 110. However, let's say we want to increase the value of lambda to favor a more simple algorithm, then we will set lambda equal to, let's say we set lambda to a large value, in this case 10, then for a simple algorithm that has a loss complexity function of 1, then the cost function is 110. Then let's say for a really complex algorithm here, even though the loss function may be, the loss function here should be 0, my apologies. My apologies here. Yeah, because as you can see, let's say we adopt the L1 loss function or even the L2 loss function. The difference between the actual data point and the predicted data point that is on the line, the best fit line here, will be 0 because it nicely fits onto the data points. Like the data points nicely fits onto the best fit line in this case because of overfitting. So where the loss function will be 0, your complexity function will have a really large value. And in this case, let's assume it's 50. Then your cost function will be your loss function plus lambda times complexity function. So in this case, it's 0 plus 10 times 50 because 0 is the loss function, 10 is the lambda, and 50 is the complexity function. In this case, you get the cost function is 500. And as compared to a previous one, the simple model, because which has a cost function of 110, and this overfitting algorithm has a cost function of 500. And the main difference is really because of this lambda. That's the determining factor. And so because of the value of cost function, we know that we should use the model with a lower cost function. In this case, the linear function, the earlier one. So even though despite the fact that it has a really large loss function, which is like 100, but because of the regularization method to avoid overfitting, we managed to like eliminate this overfitting algorithm here that has a larger cost function. And in this case, regularization allows us to adopt a simpler algorithm that is generally accurate, though not 100% accurate. And it could have a higher testing accuracy than the overfitting algorithm. Yeah, so yeah, here comes to method 2. So method 2 is called co-op cross validation, which I believe is the most commonly used method to avoid overfitting. So it's really about splitting data into training sets and the test sets, such that the learning happens on the training set is evaluated on the test sets. So to illustrate, let's look at some code here. So like in this code here, we manually divide into train test sets. So in this line here, we define a variable called who-out, which is equal to 40% of the data, the size of data. So you can see it's the integer of like 0.40 or 40% if you prefer percentage, times the length of the data, in this case, the size of the data that you have collected. And it will shuffle the data, and then after that, you define a list called testing, and it contains the first 40% from 0 to whole out. So it's the first 40% of the data points. And for training, it's the remaining 60%. So it starts for index whole out to the last element. So training, we have 60% of the data points, and testing, we have 40% of the data points. Okay, good. Okay, so now you can train model on the training sets. So let's say we define capital X training be the so-called the evidence, which is like the factors, the inputs to the algorithm, which could, for example, be like the humidity and pressure value, where we want to determine whether it rains or not. And in that case, Y training will be the label to the data points. That is like whether it did rain on that particular day or not. Like for example, X training contains the pressure and humidity in the days that we have collected data on, and Y training contains the actual event that occurred, like for example, whether it rained or not. And therefore, you can make prediction on the testing sets. So let's define like X testing be like the that's similar to X training and Y training. X testing contains the evidence, the inputs, the factors, like the pressure and humidity value on the particular days that are in the testing sets. And Y testing contains the actual event that occurred on that particular dates, like whether it did rain on that particular day or not. And now we can prediction equal to model.predict X testing. So what this line does is that it returns the prediction of this X testing here. So like X testing contains the pressure humidity value of a particular day. And then you just feed this data into the algorithm. Then your prediction will give out the predicted Y value. Like prediction could be like, it did rain on this particular day with like pressure of 100 Pascal, I don't know, but yeah. So alternatively, you can use sklearn to divide into train and test sets. So in this case, just to clarify, this is a really easy method that I think is adopted by all programmers, all machine learning programmers. And yes, in this case, you can just import train test from sklearn.model selection. And in this to separate the data, you can just write this line here. You can just define the X training, X testing, Y training, Y testing, which I defined earlier, but I can just repeat it again. So for like X training, it's really about the training set, which in this case is 60%. It gives the factors, the input to the machine learning algorithm. Like for example, for this particular pressure, this particular humidity, these are factors that can affect whether it will rain or not. And these are classified under X training. And for X testing, it's also about like the factors, the inputs, the like pressure and humidity in these particular days, they are in the testing sets. Therefore, Y training and Y testing, these lists contain like the actual event, whether it did rain on that particular day or not, in the training and testing set respectively. They will just use the train test split a function, and you just split the evidence and labels, which evidence in this case could be like the pressure and humidity. Labels could be whether it did rain on that particular day, which you could label it as 1 or 0. Like 1 means it did rain on that day, and 0 means it did not rain on that day. So it's easier for the machine learning algorithm to classify them, to separate them. And in this case, you specify this test size here, 0.4. So what this test size means is that what proportion should be in the testing sets. So in this case, 0.4, that means 40%, like the previous case. So 40% of the data sets should be classified and should be grouped under the testing sets. So 40% of evidence we group under X testing, and 40% of labels, the actual event that occur, like raining or not raining, will be grouped under Y testing. And the remaining 60% will be under X training and Y training. Then after you have split the data points, you can fit your model. So in this case, you can do like model.fit X training and Y training. So what this means is that given the label and the evidence, you try to fit the model such that it can predict future data points. So it could be like in the case of like the raining example, it could be drawing a line that best separate the two variables, the two events, whether it did rain or it did not rain. And then after that, you can make prediction on the testing sets. So you can run this code, predictions equal model.predict X testing. So you just predict the actual event that occur using the testing data sets. So given the evidence, the pressure humidity of the particular day, you try to use your model that you have fitted over here to predict whether it did rain on that particular day. So yeah, so now we have finished the whole out cross validation. We arrived to method 3, K4 cross validation. So what this method is about is really about splitting data into K sets and experiment K times, and using each set as a test set once, and using remaining data as training sets. So it may sound complicated, but let me break it down. So essentially, let's say you have a data set, like a data collection, And then let's say you want k to be 0, k to be 10. So you split your data into 10 sets. So you use, for example, use the first set as a test set first, and then the remaining 9 sets as training sets. And then you use this training set to test on the test sets to experiment it. And then after this, you get the accuracy and whatever. And then after that, you use the second data set as the test set, and the first data set and the remaining 8 data sets. So altogether, you still have 9 data sets to be a training set. And then you use this to test your test sets, to experiment on your test sets. And then after you just continue, like next case, you'll be using your third data sets and the first 2 data sets as the training sets, and the remaining 7 data sets as the training sets. While your third data set will be a test set. Yeah. So any question, you can drop in the Discord chat or the Zoom chat. Okay, so yeah, if you don't have any question at any point in time, you can just drop us a message in the Zoom chat or in the Discord chat. But do remember to ping us so that we can see the message. So we're going into regression, which is the first machine learning method that we'll be covering. So we'll be learning about regression, which is really about fitting data to a line and predicting future data. So to illustrate regression, let's talk about the definition first. So regression is a supervised machine learning task of learning a function that maps an input point to a continuous value, some real number in this case. So it's really like using a best fit line, or using the plotting a best fit line using data points that you have collected. So it's like in your physics experiment. So for example, let's say I have a beaker of water here, and then you heat on a Bunsen burner, and like at T equals 0, perhaps the temperature is like room temperature, say like 30 degrees Celsius. And then at like T equal 1 minute, it could be like say 40 degrees Celsius. And then T equal 2 minutes, it could be like 49 degrees Celsius. And then like T equal 3, it could be like, let's say 61 degrees Celsius. And then using these data points, which I think you should collect at least 6, but it does not matter. And then you can just plot a best fit line that like best approximates the relationship between the temperature and the time in this case. So do note that regression differs from classification, in that classification problems maps an input to a discrete value, like rain or no rain. But regression really maps an input to an output value that can be like any number, any real number. So like so consider this example. Suppose that you are the marketing manager of Infocom Cloud, and that you have been asked to predict how many students will be induced to join Infocom Cloud by some amount of money spent on advertising. So let f of advertising be a function that maps the amount spent on advertising to the actual number of students that were induced to join Infocom Cloud. So in this case, you collected, say, past 20 years of data. So perhaps in 1 or years, you spend $1,200. I don't know in what currency, but it does not matter. So suppose you have spent someone has spent $1,200 on advertising, and then somehow Infocom Cloud managed to induce 5,800 students to join the CCA. And then in another year, someone else spent $1,800 on advertising, and that guy somehow managed to induce 8,400 students to join Infocom Cloud. And then afterwards, in another year, someone used $2,800 on advertising and managed to induce 13,400 students to join Infocom Cloud. And of course, you have many more data points, just that I did not include all these. And yeah, and yes, you have collected all the data points that includes like the amount of money spent on advertising and the actual number of students that were induced to join Infocom class in the previous years, don't know how many years. So now the regression task is to find a hypothesis pitch of advertising that can map the amount of money spent on advertising to a predicted number of students that are induced to join Infocom Cloud. So to illustrate that, let's look at this diagram here. So let's say we plot a graph of number of students induced to join Infocom Cloud against amount of money spent on advertising using the past data point that you have collected. So for example, in a particular year, you could spend this amount of money on advertising and you manage to induce this number of students to join Infocom Cloud. Well, in this particular year, you spend this amount on advertising and you manage to induce this number of students to join InfoComm Club. And then after that, you run your regression model, and it plots a best fit line, in this case, a linear line that really approximates the relationship between the number of students induced to join InfoComm Club and the amount of money spent on advertising well enough. So yeah, okay, so now let's code. Also, before that, do you have any questions about regression or loss function? If you have any question, just join in the Zoom chat or the Discord chat. Yes. So let me hydrate myself first. Okay, so now okay, I'll be sending this link to you all in a short time after I have completed the explanation. Okay, so firstly, what we need to do when we do a problem is to import all the necessary libraries that we need. So in this case, I have imported matplotlib.pyplot as PLT because I'm too lazy to type out this whole thing. And then I have imported pandas and numpy and with the respective abbreviation. And after that, I go download a data set that's really about car fuel consumption. But we can see a data set later. And then afterward that, I use the pandas library they have imported, and then I read that fuel consumption.csv data set that I have imported, I have downloaded, yeah. And then I store it under df data frame. So let's take a look at the data sets. So the data sets contains like car models with the like different engine size, cylinders, and the transmission thing. Yeah, and all this data. But what is really important is this last column here, CO2 emissions. So for example, for this particular car, the CO2 emission is 196. Although what you need, I also do, I really don't know. And for the next car, the CO2 emission is 221, and the next car is 136, and so on and so on. So let's define another data frame, CDF, to be the column of like engine size, cylinders, and fuel consumption, and CO2 emissions. And let's see this CDF data frame. And it's really like just similar to the previous data frame. It's just like a data frame with only these 4 variables. So you can see more clearly that like with this engine size, this cylinder, this fuel consumption comp, then the CO2 emission is 196, and same for the other cars. So now we'll be doing the whole cross validation method that I have talked about on how to avoid overfitting. So in this case, because I don't want to manually divide into the testing and training sets, so I will be importing the train test suite. And in that case, you can see this code here, and I have decided that I only want 20% of my data point to be under the training testing set. Sorry, yeah, and it's not a compulsory thing to make it 0.2 or 0.4 as shown in the slides. You can use any value, but I think just avoid 0 and 1. Yes. So yeah, in this case, 20% of the engine size data will be under the testing set. So like 20% of engine size will be under X testing, and 20% of CO2 emission will be under Y testing, and 80% of the engine size, because this is the label, this is the factor, you'll be under X X training, sorry. Yeah, 80% will be under X training, and 80% of the CO2 emissions, that is the actual prediction that you want to make, will be under Y training, 80%, yeah, because 20% is in testing sets. So because we want to do machine learning, it's best if we see the relationship between the between the 2 variables that we are concerned about. So in this case, engine size and CO2 emissions. So let's plot the graph of emission against engine size. So in this case, we use the matplotlib.pyplot plot, and so we just do a scatter plot, which is like the individual data points as indicated by these blue like points here. So like, for example, maybe we have a car with this engine size, and it emitted like 250 CO2. And like with this engine size, it has emitted like probably 375 CO2, I don't know. And yes, so you just plot all the data points that you have under the X training and Y training, because ultimately that is what you are going to do your training on. You're going to fit your regressor model on this training data sets. And yes, so plt.x label is just about labeling the horizontal axis. In this case, you want to label it as engine size. And plt.y label is just about labeling the vertical axis. In this case, I want to label it as emission. And plt.show just shows the graph. In this case, a scatter plot, I think. Yeah. And then after that, because ultimately we want to plot a best fit line. Oh yeah, sorry, forgot to mention, because from this scatter plot here, it is relatively clear that like perhaps a linear graph could approximate the relationship between emission and engine size quite well. Like a linear graph that perhaps passes from here to here, it can perhaps like approximate the relationship well enough, such that you can predict future data. Like given a new engine size, what is the emission of that particular car? And then so to do that, we can do import a pre-trained model, like from sklearn import linear model. So in linear in this case, because we can see that it's probably going to follow a linear relationship. So let's define a variable regressor to be equal to linear model dot linear regression because we want to have a linear graph here. So let's do regressor dot fit x training and y training. So what this does is that it asks the Python to really evaluate to find the optimal line that can best approximate the relationship between emission and engine size. So like, because we are talking about linear line, and I believe that we have all learned that linear line is like y equal mx plus c. And in this case, m is the gradient and c is the vertical intercept. So like regressor dot fit, we just evaluate the optimal value of gradient, in this case m, and the vertical intercept, in this case c. Yeah. So like the coefficient, that is the m, the gradient, will be regressor dot coefficient, and the intercept will be regressor dot intercept. Yeah. And in this case, you can see the output here. So essentially what this tells you is that the Python has evaluated that a gradient of 38.9 will be a good and optimal gradient to a linear graph that can best approximate the relationship. And that linear graph must have a vertical intercept of 126.8, yeah, to 1 dp. And then after that, you can plot this best fit line here because you want to see how well it approximates the relationship between emission and engine size. So you can see like here we can plot the you can first plot give the scatter plot as highlighted earlier, like the blue points here, and then after that, you can plot this best fit line here. So given the x data point, that is the engine size data point, we do the regressor dot coefficient 0, that is like the m, the gradient, times the value of the engine size, which in this case is actually x, your 1 equal mx plus c. And then you plus the vertical intercept, which is like regressor dot intercept 0. So it's like m x plus c. And then you can plot this line here. And then the PLTX label is just the label of the horizontal axis, and emission is just the label of the vertical axis. And yes, and in fact, you can see that it actually approximates the relationship between emission and engine size quite well. Like you can see, it's really quite a nice fit, I would say. And yes, so after we had gotten the model, what we want is to test the accuracy, is to try to see the accuracy and see the loss function. So in this case, let's predict let's try to predict the y value based on our testing sets, the engine size in our testing set. So in this case, we let test y equal to regressor dot predict as testing. So it's like given a particular engine size that is in the testing set, we use this best fit line to predict the corresponding emission test y. So using this, we get a list of like the emission value. And then we want to find the mean absolute value, which is technically your L1 loss function, because it involves the absolute difference between the actual value and the predicted value. So in this case, your test y is the predicted value and y testing is the actual value, because that's the data that you have collected and classified under and group it under y testing. So yes, this line here is actually your L1 loss function. It's also called mean absolute error. So it's 24.89. It's actually quite a good thing, I would say. And then for the and then you can also compute L2 loss function, which in this case is similar. It is like the test y, which is the predicted value of CO2 emission minus the actual value of CO2 emission as collected previously from your data sets, and you square it, the star square, yeah, asterisk square. Yes, and then you just compute the mean, the average of all these sum of the square of the difference between the actual value and the predicted value, and then you get 1159. And yes, I have come to the end of this code, and okay, so I will be sending the link to you all now, and you all can you can create a copy of the code and try to change any parameter, perhaps like the test size. You all can change to other value, but try to keep it between 0 and 1, because I'm not really sure what will happen if you exceed this range. And yes, you can see what will happen to your accuracy. And you can also experiment with like Matplotlib and try to figure out how to sketch a graph. Yeah. But also, if you have any question, you can also about like regression and also like loss function and classification in general. You can also drop a message in the Zoom chat or the Discord chat, and we'll be trying to answer the questions. Yes, thank you. And yeah, you have 10 minutes to read through the codes and think of any questions they want to ask. And yes, you can also take a break. Okay, so the time is now 3:31. I will pass the time to 18.
Thank you very much, Iwan, and I hope everyone has been able to understand the past hour. Is everyone able to hear me? Thumbs up. All right, great. So I'm Yikting, and I'll be covering Perceptron Learning. And what Perceptron Learning is basically building on a bit of the techniques from previously. I'll start off with this very, very complicated diagram that you see here, and you'll be thinking, boom, you look at this and you're like, oh my God, how am I ever going to understand this? All right, don't worry. Let me break this down to you slowly. And by the end of this entire time, this diagram will be nothing to you. All right, so at the very start, this is a very simple perceptron. This is what I call a perceptron. And you can see it's kind of like I guess it's kind of tree. You see that there are 3 roots here, and the very bottom is inputs. So remember just now, Iwang touched on inputs and how they are like different kinds of inputs. And these, I guess, 3 inputs go into the middle, where the middle is kind of like the calculation, where the calculation happens. And then this produces one output, or in this case, is one output, which is this top stem at the very top. Now, there are a few area of focuses that we're covering, and Iwang has actually covered the very first area of focus, which is inputs. So now I'll be moving on to more of how the inputs move into this very middle of the circle, which is more of the computation that happens. And this computation goes through 2 steps. So the very first step is weights, which I will term as area of focus 1. Are you all still able to hear me because my internet cut off? Mic test. All right, because it says trying to connect here on Google Slides, no problem. All right, so the very first area of focus will be on weights, and the very second area of focus will be on activation. And these are the 2 areas that I'm covering when I'm going through perceptrons. So the very first thing we all love when it comes to computer science is very old, boring definitions that you heard for 1,000 times. What a perceptron is, it's kind of like a neural, it's a neural network unit. So you might have heard of something called neural network, which I'll go in later. This is kind of like an artificial neuron. So just like the diagram I've shown earlier on, this does a certain computations in the middle based on these inputs, and it produces the output at the very end. And hence, a lot of times this is used to detect features, and this makes your computers basically smarter. It's all coming from all these mathematical computations that you do in the middle. And with maths, as I mentioned, we love maths in machine learning. Here's a little meme, because you can never run away from maths when you come into machine learning. And so here's a very huge equation that once again will look very complicated, but maybe let me start off simple. So that I guess that's kind of like 2 lines to equation. This very first line basically means that I'm multiplying, I'm having a few inputs, right? Remember just now in the tree, I have like kind of 3 inputs. Let's say I take the very first input, which is X. Let's say I take the very first input and I say J is location 0 because we come from 0 in computing. So let's say I take the very first location of the input and I give it a particular weight. What does a weight mean? This is when I'll go through and I'll give an example. So for example, let's say your input is a value of 5. Let's say your value is 5, and with that, let's say I have 2 different nodes with 2 different with 2 different weights, but I have the same input. So both of them have the same input of 5. The very first one might have a weight of 10, and hence when I do the computation, it will do 10 times 5, which means it will become 50. But at the same time, the other side, the input is still 5, but the weight is 2, and hence the computation ends up being 10. When I compare these two nodes, you can see that the one with a heavier weight will have a bigger weightage. That means it's more important when it comes into calculation. Because once again, the very first node, my final computation is 50. Second node computation is 10. Therefore, the very second node, when I add up the sum together, the very second node will be taken into consideration more in a sense that is more important than the first node. So basically, some of the inputs might be more important than the very first one. An example is, let's say I'm doing an essay test, right? Maybe whether I eat before the test, that input is maybe not that important. Or let's say how much I study before the test, you know, that second input is really important when it comes to determining your essay grades. So this is when your weightage changes around. And with that, this is one input, right? So for every single input, I will have a different weight. So for example, when I have input 0 for x in position 0, I have an inputs and our corresponding weights for it. And similarly, for inputs 1 at x, position x, I have a corresponding inputs and I have corresponding weights. And what I'll do when it comes in the middle of the calculation is that I want to add up all these weights multiplied by the inputs. Okay, I repeat, I want to add up all these weights multiplied by these inputs, and then this will create a computation at the very end. And this is basically what this second line means, which is kind of a product of all the inputs and all the positions multiplied by their corresponding weights. So with that, I've covered how the different inputs coming from AOF1 enters and now it's determined by the weights at AOF2. All right, moving on. So now I want to compare, and I want you to think of an analogy, right? Is that actually this kind of a perceptron unit can be something like a light bulb. All right, maybe not these LED light bulbs that you have nowadays, but think of those ancient light bulbs that you only have a filament or something, and you connect electricity to it. So it either turns on or off, right? There are two options to light bulbs. It either turns on or off. All right, so think of a perceptron unit in that way, that an output produced will have two possible outputs. It's either 1, which means on, or 0, which means off. So remember, perceptron unit, think of light bulb. Once again, coming back to maths is something that we all love. This is the equation that we saw just minutes or seconds earlier on, right? But this is kind of complicated and kind of big equation that nobody really likes to look at. Because imagine dumping all these equations in scientific papers or what, it'll take up like so long. So let's screw this equation, throw it away, and this is a much simplified form. This is actually what we call a sigma notation. So this is actually something that you might learn in JC. So what this means that is basically I'm calculating the sum of all the weights, which is W, and all the inputs, which is at X. And what I'm doing is that I'm increasing it until the number of, I'm increasing according to the number of inputs. So the number of inputs is M. I start off with I equals to 0, where the weight is, I equals to 1, where the weight is at position 1 and the input is at position 1. And then I increase I by 1, which means that now the weight is at 2, and then the input is also at 2. So what it's doing is basically this. It's the exact same thing, right? It's basically I'm adding up the weight and the input at a corresponding point, right? It's just that I simplify this exact same formula. Now, what my activation function does, I repeat, that is area of focus 3, right? What my activation function does is that it checks whether it's more than a certain value, all right? Moving down to this equation. So you're gonna see a lot of maths, but rest assured, you know, a lot of them are easy to understand. So once again, think of the light bulb, right? There are two chances of it. It's either turns on or off. The fact that it turns on is that we want to check whether the computations we made is more than a certain limit. In this case, if you look at this equation, W dot X, this is actually referring to this sum of weights and inputs that we calculated earlier on. But then there's this new term called B. And what is B? B is what we call a bias. All right, I'll give you a bit of time to absorb at this point. All right, we've covered the activation function. We've covered adding the weights and the inputs. All right, now I am introducing a new term called B. And this is basically where we set the threshold of whether the light bulb turns on or off. All right, so if you look at this equation, I'm basically rearranging B to the other side. Initially, W times X plus V is more than 0, right? In this case now, it's the same thing. W times X is more than negative B, right? So in this case, I'm basically trying to see whether my product, my summations of my weight and my inputs are more than this certain level of B, right? If it's more than this certain level of B, then my light bulb will turn on. Otherwise, my light bulb will remain off. Think of this like, I guess, electricity flow. maybe you have just a little bit of electricity passing through, and with that, that is insufficient for a light bulb to turn on. So your light bulb remains off. It's only when you have your amount of electricity passes a certain threshold that your light bulb will turn on. So hence, your weight times x must be more than this b, or in this case, negative b, in order for this neuron to activate. So otherwise, it will remain off and your output 0. This is what we call actually, there's a terminology which is called binary step function. All right. You'll be learning a few functions. This is one of the activation functions, and it's called a binary step function. If you look at this graph, all right, this on the x-axis is basically our inputs. So it's the weight times x plus the bias. Basically, it's for us to set our limit, our threshold, right? So weight times x equals bias. If it is more than 0, you can see that my light bulb turns on, right? Let me annotate. Give me a second while I get out my annotations, and you can see if you can see my mouse cursor, if I'm more than 0 in my input for my weight times x plus bias, then my light bulb will turn on, which is over here. All right. Otherwise, if it's less than 0, then my light bulb will remain off, which is 0. So this is basically the mathematical model just now. Now moving on, so once again, I want to reiterate that you can think of this like a light bulb. Keep thinking of this when you think of the idea of a perceptron. There are other kinds of activation functions actually. Wait while I clear my drawings. And there are other kinds of activation functions. So instead of just having a light bulb, right? Actually, the computer scientists have come up with a lot of new kinds of activation functions. So there's this one known as a linear activation function. In maths, you might be aware of the graph y equals to x. And this is basically y equals to x. That means as your input increases, then your output will increase. Otherwise, as your input decreases, your output will be decreasing. And this happens on a linear scale. That means every unit of input is equal to every unit of output. And basically, that means that your output can vary. It won't be just a 0 or 1. It will be more of a slow flow upwards. And there's another kind of activation function, which we call a sigmoid or logistic activation function. Right, this is slightly more complicated, but once again, don't worry. Let me get my annotation tool out, and you can see that actually around the point 0, right? Let's say I split this into 2 intervals, right? Let's say I split this into 0 to 3 and 0 to 6. All right, this very left marker on the bottom is 0, the middle one is 3, and the right one is 6. Let's say I increase my input. Well, once again, reiterating, my input is w times x plus b. Let's say I increase my input, which is 0 to 3. I increase it from 0 to 3. I want to see how much my output changes. So I draw a dot here. I draw a dot here on my graph, and you can see that actually my output changes quite a bit. All right, this is how much my output changes, which is over here, output. I can't write. Okay, I'll put it as O, right? So O is how much my output changes. Now I compare 3 to 6. Let's say I increase, it's the same interval, right? All this is 3. It's just that I'm increasing it from 3 to 6 instead of 0 to 3. When I'm increasing it from 3 to 6, you can see that actually my output doesn't change that much. It changes as a much smaller scale. So what this does, it means that as your input increases, right, the amount of how much it affects your output, the value decreases, right? Once again, 0 to 3, you can see there's a big difference in output. However, 3 to 6 is a much smaller difference. The reason why a lot of computer scientists use Sigmoid or logistic functions nowadays is because they want to focus on the small details that they are tweaking at the very end of the model, right? So when you're nearing your end, when you're nearing a very nice, I guess, Sigmoid or logistic curve is that you might want to change your output a bit more so that your model will perform better, and it'll kind of vary better when it comes to training your model. Hence, Sigmoid and logistic functions are used much more nowadays. Okay, any questions at this point? So once again, I've covered perceptrons, I've covered weights, and now activations. Okay, there's a lot of things that you have absorbed, so take some time and think about it. All right, moving on. That was a very nice water break for me. Welcome. So now that we have perceptrons, right? We know the idea of perceptrons, which is once again is the one unit, three inputs heading into the one computation and then creating that one output. However, perceptrons are quite it's quite basic, I would say, because it can only create one kind of computation. And in the sense of AI, you think of AI being those kind of driverless cars or those big crazy ideas. But you know, a lot of times a perceptron is just a simple computation. Hence, this is where this meme comes in. It says perceptrons are too linear. We must go deeper. More than having a single perceptron, we need to have more than one perceptron. And this is when the idea of, you know, you have a perceptron as a kind of a baby dinosaur that you know, is something very simple. right? And then you move to this new thing called multi-perceptron. It's where you stack up different perceptrons, and I would compare this to a giant dinosaur. So a mini dinosaur is a single perceptron, and a giant dinosaur is more of a multi-perceptron that's so much more complex and can do so much more functions. And similarly, a similar naming for this will be artificial neural network. So new terms again, perceptron, moving on to multi-perceptron, or what we term as a multi-perceptron network. And similarly, it's termed as an artificial neural network. All right. So more definitions for you. A neural network, I would say, kind of acts like a brain, right? So a lot of people compare this, do this analogy that neural networks work like brains, although a lot of professionals deny this otherwise, but I still use this analogy, which is quite good. If you study bio, although I don't, if you study bio, you will know that, in your brain, that there's a lot of neurons actually connecting up, and these neurons either fire or don't, which is where the binary step function comes in, right? So in this case, in a brain, there are like, don't know how many neurons, there's so many neurons that can you count? I'm not sure. But either way, so these neurons add up and this create this complex thing called a brain. Similarly, an artificial neural network is based on this collection of units and nodes. It's based on these perceptrons that are piled up together, and this forms this artificial neural network. So it's kind of like artificial neurons, but you combine them to create this one big network. All right, let me take a breather and wait for my slides to load. So at this moment, think about artificial neural networks, and moving on, artificial neurons. How am I going to define the neurons themselves? Basically, a neuron is kind of like a perceptron. It's just that the very basic first neuron that came out as a perceptron. Nowadays, there's a lot more that you can change about a perceptron. Maybe there are different kinds of sigmoids. There different kinds of activation functions and biases that you can change along the way to vary your kind of neurons. And I guess this is something you can search up, because you shouldn't stop learning about AI after this process. You continue on. So these are some of the things that you can explore of the different kinds of neurons that we now have. So coming back to this very simple model that we started off from the very start of this workshop. Now I just want you to turn your head, boom, and you look at this. You see this? I just change this orientation of this neuron, and now you can see that I stack up all these neurons, and this creates this very complex model that we see from the very beginning. If you compare slide 93 to 94, yeah, we are slide 93, a lot of content. Slide 93, you can see that the inputs, right, it's basically the same thing as the left side. You can see basically this is one perceptron, this one circle. Once again, let me head to annotating. This one circle is one perceptron, right? And then you have outputs coming out of it, okay? And actually the outputs lead in, and the outputs are now considered as new inputs to other perceptrons, right? So these are outputs coming from, I guess, this row of perceptrons here, and now it's coming into this new perceptron over here as inputs, all right? And then from this new perceptron, you take this inputs, do some computation, and you produce these outputs, which once again turn into inputs for other perceptrons, and so on and so forth. So basically, you're stacking these perceptrons so that some inputs, some outputs go into the new inputs, and so on and so forth. And this is where you get your neural network. All right. I'd like you to think of another analogy, right? Is that, it's just like a human body. When your mind processes, you're actually processing a lot of your human information from, I guess, your nose, your mouth, or I don't know, your touch, right? It's similar to your senses. Is that all these are the very inputs that start off, that are at the input layer, right? They are all these very basic, the very first things that we receive when our brain processes information. But slowly inside the brain, there's a lot of complex networks that happen, a lot of computations that happen, and this produces an output which I'll compare to your action, right? What we do in real life. For example, I'm thirsty. My brain tells me I'm told that I'm thirsty, and then thus I will drink my water, and that's where my output goes, right? But in the middle, there's a lot of computation that goes in our minds that produces the output. So I'd like you to think of the input layer as the different factors that you kind of input in the model, similar to the essay idea just now, maybe the number of hours you sleep or something, or the amount of homework you did. And then this produces an output which predicts your score. But in the middle, the hidden layer is kind of the computations that happen. All right. So the hidden layer, as I mentioned. And another definition, while I clear out my annotations, my definition is that this is basically the layers between the input and output, and it does a lot of it takes in a set of weighted inputs and then produces the output, like I described earlier on, basically. All right. So I've come close to the end of my side of the theory part. Take another breather while I take another water break and think about it. Yeah. Once again, any questions, drop it in the chat, or if any questions pop up at the end, feel free to text us on Discord. Ping us, please. Yes, all right. So now moving on, I'll be moving to some demonstrations. Another meme. Don't know why we love memes so much in this workshop, but yeah. All right, so this is a demonstration of it's kind of a simulation of a neural network, right? So this is a pretty fun website, I would say, to play around with, and I'll give you a chance at it later, but first, let me go through. All right, you have a kind let's say we have a classification problem, as Iwan has described earlier on. We have a classification problem, which we have, I guess, a few kinds of inputs. In this case, we have orange inputs over here, and we have blue inputs over here. And what we are doing is that we're going to try to classify these two groups of inputs in different groups. So let's say I have a new point over here, right? Am I going to classify it as blue or orange, right? If you think about it, you would classify it as orange because let's say you're doing a grouping, you might draw a line around here as your border, right? And your right side will be blue and your left side will be orange. So if you have a new point over here, then it'll be classified as blue. This is what we think theoretically as humans, right? But as machines, you need to do computations for this. And hence, this is when your neural network comes in, right? If you look at this, this is basically your different hidden layers and, oh, sorry, annotations got turned off. So this is basically a different, it's a neural network, right? So you have a few inputs, maybe let's say you have two inputs in this case, and you have a single neuron, and you have two hidden layers, or maybe let's say, let's make it one hidden layer, all right? Oh, I can't make it, oh yeah, okay. Let's say I make it one hidden layer, all right? And then let me train my model. If you look at the top left, there's a play button, which is to train your model. And when you train the model, the output comes out corresponding on the right. So you can see that immediately, it kind of produces a very nice distinct line. And you can see that it's grouped into two places, the left side, which is orange, the right side, which is blue. And this shows that the classification is done well, right? Because all the orange points have been classified into orange group, all the blue points have been classified into a blue group. But in life is not so easy. There are a lot of different trends or different factors, you know, that will come into play when you do a lot of these data. Your data will not be as simple as, you know, classifying it into two groups. So maybe your data is something like this. Maybe you have to draw, you can't draw a single line in this case for you to, you know, separate this into two groups, right? So maybe you have to draw two lines. If I were human, I would draw this as two lines, right? And I would say top left orange, bottom right orange, top right blue, bottom left blue, right? I'll split this as a human. I'll think of that, right? What if I run my artificial neural network with a single neuron, a single hidden layer? What would happen? Make a guess. 3, 2, 1. Obviously, the machine learning model wouldn't perform really well. You know, it will kind of draw a single line, right? Because I only have a single neuron. I can only do a single calculation of a single weight, or I don't know. I can't. You know, put that input into another input and make complex calculations, right? I only have that one single perceptron. And hence you can see I've gone pretty long into training the model, but this is pretty inaccurate because, you know, I'm classifying the blue points here kind of correctly, but in this case, I'm classifying the blue points as orange, and this is not something that I want. And in this case, you can see that also the confidence of the classification is also highlighted by the color. In this case, it's faint orange, it means that it's not classified very well. Although the blue side is classified very well, but not the orange side. In this case, I guess the accuracy would not be very high of the model. So in this case, maybe I want to increase a hidden layer or increase a neuron. Let's see how my network would do. Slowly let it load, let it load, let it load. Ooh, this is kind of more interesting. You can see that it creates two straight lines down. I'm actually running this live, right? Because I kind of didn't plan this, but you can see that it kind of comes out with two lines. It's still not the best, actually, because although most of the orange points are classified correctly, and most of the blue points are classified correctly, there's still a few anomalies like these blue, I don't know, blue dots here that are classified into orange. With this reminder is these dots are actually input points, right? So these inputs have I guess, certain X value and a Y value, and when you classify them, that's when you draw the line, all right? So each of these points is a certain input. So some of these inputs are not classified correctly. So what I want to do is I want to increase more neurons and let's see how this goes, right? Still not very well. Maybe let's say I increase the number of hidden layers. Now the simulation run, slowly running. So you can see that a lot of times in machine learning, right? I create this, right? See that turning of those curves. Basically now this, I would say, is a much more accurate classification thing, right? As I mentioned, we'll probably draw two lines down, but similarly, this classification is able to classify the orange points to orange groups and the blue points to blue groups, which means it's really accurate. All right, but why don't we make it much more complicated? What if we have this, right? If we have just 3 hidden layers and 3 2 neurons, you know, how would this work out? So now I want you to spend some time and play around with these different buttons. There's a lot of buttons on the screen that you can press and toggles that you can toggle around. So try and play around with it in the next, I would say maybe 10 minutes, or maybe I'll give you around 8 minutes, and then you can see what kind of conclusions you can draw from this. And whatever you learned, please send it into the chat. It's a very long link. Don't worry, it's not a scam. It's a simulation to TensorFlow. TensorFlow is actually one of machine learning models. So feel free to spend the time, tinker around with the different inputs, outputs, everything. See you in a bit. Remember that there are a lot of different types of things that you can try out. So on the left side, you have the test to train ratio stuff. There's the inputs that you can change. Middle is your neural network that you can change. And at the top, there are much more parameters. So feel free to press those buttons and tweak them around. I'll give you around until 4, and then we'll move on. Once again, if you have any questions after exploration, feel free to drop them in the chat. I hope everyone has had a great time trying out the different parameters and the different inputs inside this simulation. While you're having a break, I heard opposite side, Ian and Iwan trying it out. And, oh my god, wow! Even they're impressed. So even after this workshop, continue exploring on this website, continue trying on the simulations, and then look back at this, right? Okay, so I have this very complicated, spiral looking thing, and I want to classify this into blue and orange. So let's say I run it with, just 3 hidden layers and I guess 2 neurons. You can see that it's kind of not doing its job. It's drawing a weird line that doesn't even really fit. Okay, it's quite badly classifying because most of the blue points are classified wrongly into the orange group and so forth. What if I kind of increase this to 7 neurons and I play this? You can see that maybe it does kind of better. It looks slightly better, but maybe not. All right, I think the key is that I need probably around 6 hidden layers and maybe I don't know. I just spam neurons, right? Okay. And you can see the complex number of lines going in. If you know the lines, right, you can see that it says that this is kind of like the output from 1 neuron. So in this case, it might be using something like a linear or a sigmoid activation function, and the output that comes out is this weight, right? And this is the kind of how important an input is that goes into another. How important this output is that goes into another input, right? Let's say I run this now, and let's see, I kind of spam 6 neurons, and it still doesn't work. It's kind of sad. It is kind of sad. So, try and play with this around in your free time. I think the key is to really dump the amount of neurons I have to the max and see how this goes. All right. Meanwhile, while this thing is loading, I want to highlight to you something which is called the loss. If you look at the top right, there's this thing called the loss, right? So linking back to this, to what Iwan mentioned earlier on about L1, L2 loss, you can see that basically I'm trying to reduce the, I guess, kind of difference between the different, the expected output and the actual output. I'm trying to reduce that difference. So there's the actual loss that I'm trying to reduce. In this case, you can see that this is the test loss and the training loss, which are put here. And this is once again, the data that is kind of area of focus one that Iwan focused on. So to have a good model, it's not only about the neural network, it's also about the inputs that you kind of put in, right? So maybe let me dump a few more, and then this should work. Okay. So you can see that actually some amazing shapes start to come in. All right. Okay. The fact is that my trial was kind of destined to fail. So feel free and try this out back at home and try and see how many hidden layers or how many neurons you need to kind of fix this final number of features. Okay. And then another thing is also the training to test data, which is something also Iwan pointed earlier on, which is the train test split, which might be something you want to edit. And learning rate, activation, regularization is some of the stuff that you might want to do further research on. We won't be covering them today, but there are some things that are kind of important. So afterwards, I hope you have the time to experiment with ANNs. Give you 2 seconds. That this mean you versus the guy she asks you not to worry about, and laugh at our computing jokes. Now we're going to move on to code, right? So after the simulation, right, you know how kind of like neural networks work, but in real life, simulations are not that easy, and it's much easier to write code and modify your model to what you actually need to. So another thing I want to highlight, right, is that ultimately if I choose a very simple classification idea, if I choose a very simple thing to classify like this, orange one group and blue one group, it's quite easy to run this 6 hidden layers and I don't know how many neurons network on my thing, right? And you can see that it kind of classifies it well. But a lot of times, having more hidden layers or having more neurons does not mean that this will become a good model. As you can see, this has started to overcompensate a little. If let's say I wanted to draw a line, if I was a normal human, if I was not a, I guess, weird human, I would draw a line. Oh, that's a very bad line. I'll draw a line in the middle here, right? And classify these two groups. But in this case, you can see that this machine actually kind of overcompensates for it and it kind of draws a line over here. That I would say is kind of slightly overcorrecting to the model. So let's say I have a point here predicted, which is supposed to be orange, but in the end I predict it as blue, right? So this does not mean that increasing your hidden layers and increasing your neurons definitely helps make your model better. And at the same time, increases your computation time. And computation time is really precious when it comes to training a model, because a lot of time you might take a day up to a day to train. So it's you better make sure that I guess you spend the minimum time that you need in this when it comes to training the model. All right. So so moving on to the code. This is the actual code that I will once again send you the link later. This is called the breast cancer model from sklearn, right? So this breast cancer model actually has some kind of inputs and some kind of output that I'm trying to predict, right? So the very first thing is cancer keys. I'm over here. I'm loading this. I'm loading this. If you're not, I'm not sure whether the earlier Python workshop covered this, but this is kind of like a module. And it's loading this data set called breast cancer. All right, I'm not trying to load cancer. I'm trying to load this data set called breast cancer, and this data set kind of confirmed has some information on predicting this. Sorry, let me run this at the start. Kind of predicting my output, right? So with that, I want to press cancer.keys. What this does is it prints me what is inside the data set. And inside the data set, you can see there's a few things, which is data and targets. These two things are the main things that I want to focus on today. Data is kind of like the inputs you have, right? So maybe each cancer patient has some kind of characteristics that make them a likely cancer patient. And there's a target that you're trying to reach, which is to check whether a patient has cancer or not. I would say this is kind of a two-group classification, which either you have cancer or you have not, kind of case, but you're using the data and trying to classify that and make that happen. All right. In this case, now I'm going to print cancer data.shape. And this is actually trying to see how many kind of input points I have with how many features. The features are kind of like characteristics. So maybe I have, like, let's say a lot of characteristics. Age might be a characteristic. Maybe, I don't know, height might be a characteristic. Whether male or female might be characteristic. Yes, male patients might get cancer as well. But anyways, so this breast cancer as well. But anyways, so that I have finite 9 data points in this case as inputs, and I have 30 features for each of them. And I split them in this case into X and Y. So X is the data that I'm inputting, and Y is the target that I'm trying to predict. If I print out Y, you can see that there are actually a lot of zeros and ones. These are, I guess, 5, 6, 9 of the outputs that I'm trying to predict whether a patient has cancer or not. If a patient doesn't has breast cancer or not, if a patient doesn't, it'll be 0. If they do, it'll be 1. All right. Moving on, this is the very simple code that I think Iwang has explained earlier on. This is the sklearn train test split kind of function. So what it does is that it splits my X and Y, X remember being my inputs, Y being my output that I'm trying to predict. It splits this into the train sector of data and the test sector of data. And with that, afterwards, I try and scale up my data. So I use this function called standard scalar. Once again, Iwang mentioned, this is makes it to standard deviation of 1 and mean of 0, so that it ensures your data is kind of distributed well, right? So this is kind of pre-processing of data. And finally, I try and fit my transformations to data over here. Now, this is where most of the magic happens, right? Up to now, if you don't understand much of it, don't worry. I will send you the code. You can go back home and think about it. But this is the more important part. It's the more magical part, because I'm importing, all right? I'm importing this classifier function from sklearn neural network. And with that, I can simply create a classifier. I can create a neural network with that. In this case, in the very first here, I'm going to have, let's say, 2 hidden layers, and each hidden layer has maybe, let's say, 5 neurons in this case. All right, this could be one of my neural networks I'm trying to create. Otherwise, I might have, let's say, 3 hidden layers, and the first one is 30 neurons, second one is 40 neurons, third one 50 neurons. This could be another kind of MLP classifier that I'm trying to create. And once again, MLP refers to multi-layer perceptron. This means that I'm stacking on the perceptrons, and each one is kind of like neuron, right? So with this, I'm able to create this template for the model. With this template for the model, I input in my data, which is my X train and Y train data. Once again, Y train is to predict, X train is your inputs that you're trying to, your characteristics of a patient. And then afterwards, you do a prediction and you can come up with a matrix to see, metrics to see how accurate your model is. All right, so some of the metrics are true positives, false positives. This is basically a confusion matrix, which means that if you're true positive, this means that a patient actually has cancer and you predicted the patient's cancer correctly. And this is kind of good for the machine learning model. That means it's predicted quite well, right? But otherwise, there are a few other kinds of data that you might try and get. So I won't be covering in this course today, but I'll tell you how you can learn about that later. And other kind of metrics that you can learn about is precision and recall and F1 score. And these are some really important data statistics that you retrieve from your confusion matrix and metrics. I keep pronouncing it as matrix. Oh, actually, confusion matrix works as well. Anyways, you produce that, and at the very end, you can see how accurate a model is. All right. So with that, we have completed our coding time with the artificial neural network. I'll give you around 5 minutes to take a look at the code, and I'll take another break. All right. See you in a bit. Any questions? Drop it in the chat. Okay, guys, hope you have managed to learn a lot about perceptrons and perceptron learning, which is basically piling up perceptrons. Ian will do a kind of consolidation at the end, but some exploration if you want to learn about F1 score or accuracy. I should kind of cover it in my Intro to Machine Learning course last year, also in Building Blocks. So I'll send a link at the very end of this workshop if you want to learn more about it. At the same time, normalization might be something that you're curious to learn about. So that one you can do some more research, and we hope that with this you also have gained more knowledge and are more interested to continue your pursuit in neural networks after this. With that, I'll be passing on the time to Ian.
Okay, thank you, Ik-Ting. And once again, if you have any questions, please post it in the Zoom chat or ping us in Discord. So now I'll be going through a common supervised learning model used called support vector machines, otherwise known as SVMs. So here's a brief outline of what are we going through today. So what are SVMs, how SVMs train, how SVMs carry out multi-class classification, as well as kernel SVMs. So SVMs are mainly used for classification. Given a set of inputs, it hopes to find the optimal boundary separating the classes. So all of the green lines here on the picture on the right can actually act as boundaries, separating the blue circles from the red squares. But these are not optimal boundaries, whereas something like this red line would be considered the optimal boundary. But how does the SVM know if the boundary is good or not? So SVMs use something known as support vectors to determine if a boundary is good or not. And if you recall, the SVM actually stands for support vector machines, so it's based on support vectors. Yeah. And support vectors are the inputs that are the hardest to classify. So on the picture from the right, you can see that this red circle here is closest to the bulk of the other class, which is the gray squares. Hence, it is considered a support vector, whereas the two gray squares are closest to the red circles, so they are also considered as support vectors. So to get the optimal boundary, the SVM must then find a boundary that gives the maximum margin or distance away from the support vectors. So as you can see, the boundary in the middle on the picture here has the maximum distance away from the support vectors of both the red circles and the gray squares, whereas any other line, such as a line a bit above this line here, although it would have a larger distance away from the gray squares, but it will be nearer to the red circles, hence it is not the optimal boundary that the SVM wants to find. And actually, the boundaries that I've been mentioning earlier on are called hyperplanes in the terminology of SVMs. Since inputs may not be just 2D, but they can be like any dimensions like 7D or even like 100 dimensions. So we call them hyperplanes. And for n dimensions, the hyperplane or boundary will be n-1 dimensions. So if you look at the pictures on the right here, we see that in a one-dimensional case, where the inputs lie on a line, the hyperplane is just a point, which is 0-dimensional. And in a two-dimensional case, the hyperplane is a line, which is 1-dimensional. And finally, in a 3-dimensional case, the hyperplane is a plane, which is 2-dimensional. So for input of n dimensions, also written as x1, x2, all the way up to xn, the equation of the hyperplane would be given by a w times x plus b equals to 0, which Ting mentioned earlier on. So it's something similar to that, where the w is like the weight for each of the inputs, and b represents the bias of the SVM. And this can also be written as the product of the weights and the inputs, like w1 times x1 plus w2 times x2, all the way up to wn times xn plus b equals to 0. And the weights correspond to the significance of each of the inputs in contributing to which class it is classified as Ting mentioned earlier on as well. So the larger the weight, the more important the input is in determining the class of the object. Yeah. So the training of the SVM is used to fine-tune the weights and the bias in order to get the optimal hyperplane with the maximal margin away from the support vectors. So if you have this set of inputs here, our aim is to separate the blue ovals on top from the red rectangles on the bottom. So the SVM will train, like maybe starting with this line, and then it will train again. Every time it changes its the weights and bias in order to finally get the optimal boundary, which is this one here. And then in this case, can anyone spot the support vectors, which I accidentally showed just now already? So it will be this blue oval here, since it's nearest to the red rectangles, as well as these two red rectangles, as they are closest to the blue ovals. Actually, if you notice how the SVM is trained, if it's based on the distance away from the support vectors, that actually means that the other inputs, which are non-support vectors, in other words, this patch of blue ovals here and all of these red rectangles, they actually don't contribute to whether the boundary is optimal or not, because the optimal boundary is solely based on the distance away from the support vectors. Yeah. Now that we have the weight matrix and the bias, how does the SVM classify any unseen inputs which are not in the training nor test data? So using the weights and the bias which are determined already, for an unseen input, let's call it like x prime instead of x. If w times x prime plus b is greater than 0, this means that the point would lie above the hyperplane. And in this case, it will be classified as a blue circle. Whereas if the calculation of w times x prime plus b is less than 0, then the point would lie below the hyperplane, and then it will be classified as a red square. The larger the magnitude of this value classified, the further away it would be from the hyperplane, which means that the model would probably be more confident in classifying the input. So say like if you calculate w times x prime plus b to be like 10, then maybe it lies super far away from the hyperplane. So the model will be confident in classifying it as a blue circle. Whereas if the calculation was 1, then maybe it lies like super near to the hyperplane. So the model may not be that confident in classifying it as a blue circle. And here I'll pause for a short while to let y'all take it in while I take a short water break. Okay, let me continue now. So in the previous parts, we were only focusing on the case where there are two classes. So this is also known as binary classification because binary is like 2. Yeah. So, but what if we need to separate the data into more than 2 classes, say like 3 classes or 4 or even more than that? So how would the SVM classify the inputs? So this is where the multi-class SVM comes in. And multi-class SVMs use an approach known as the one versus all method. So let me explain what this means. Suppose we have these 3 classes, red, green, and blue, and we need to separate each of them such that the SVM can classify an unseen input. Since the SVM only knows how to do binary classification by coming up with a hyperplane, so the SVM will carry out binary classification a total of 3 times, and this is how it will happen. Firstly, the SVM will consider the red class as a class by itself, and it will just count the blue and the green class as something like the gray class, which is also like the not red class. And so the SVM, after training, we'll come up with a hyperplane that separates the red class from the blue and green classes or the gray class, coming up with this red boundary. So if you take a look at the original data, it looks something like that. And now we need to settle the green class. So we take the green class as a single class, and then we combine the red and blue classes into the sort of gray class. Then we come with the boundary that separates the green class from the gray class. And then I think you can see where this is going, but we do it once more to separate the blue from the gray class to come up with the blue boundary. And now we see that the final boundaries and the data looks like this. So for an unseen point, like say this yellow point here, how would the SVM classify this point? It will first check whether it is a red point or not. And since it lies on the other side of the red boundary from all the red points, it is probably not a red point. And then the SVM checks if this yellow point is a green class, which since it lies on the other side of the green inputs, is also not green. And finally, since this yellow point lies on the same side as all the blue inputs, the SVM would finally classify this point as blue. So some of you may have noticed a problem, which is that what if the data or the input falls in one of the overlapping regions? So actually you can search this online, but basically what happens is that, say for this yellow point over here, since it lies on the same side as the green inputs as well as the blue inputs, the SVM will calculate the probability that is each of the classes, and then say if the probability that this point is green is like 0.3 and the probability that is blue is 0.7, then the SVM would take the one with the higher probability and then classify this point as blue, since there's a higher chance that it is blue. And I'll let y'all take some time to digest this info, and we'll start a few seconds later. Okay, so let's continue now. So all of the previous slides will make the assumption that the data is linearly separable. In other words, like if you see this picture on the left, we can get a hyperplane which cleanly separates both classes. But in the real world, data is more likely to be quite complex, like this picture on the right here. So the data may not actually be able to be separated by a line. So in this case, how would the SVM create a hyperplane to classify inputs? And this leads to another type of SVM known as kernel SVMs. If you look at the following data, it looks like on the left side, it looks like there is no possible line to separate the data. Like if we cut here, even though all the red inputs are on the one side, like there can still be blue inputs on the other side. And it looks like this data is very hard to separate. So how would the SVM do it? But if you observe the data carefully, if you look at the point 0, 0, which is around the middle of the picture, you see that the red points, the red triangles, are much nearer to this point than the blue circles. So what we might think in this case is to transform the features. Instead of just using the original features, we want to transform them such that the data can then be separated, such that the transformed data can then be separated by a line. And in this case, we might use something like, we might square feature 1 and square feature 2. So since the features, both feature 1 and feature 2 for the red triangles are relatively small because the points are near to the origin. So after you square them, the values will still be small. And so in the transform data, the red triangle still lie near the point 0, 0. Whereas the blue circles, since they lie further away and their features have a greater magnitude, so after you square them, they will lie much further away from the point 0, 0. And this allows the SVM to create a boundary or a hyperplane that separates the red triangles from the blue circles. And this is done using a kernel, which helps to transform the data. Yeah. So now I'll be going through two of the more common kernels. And the first one is known as the polynomial kernel, because it's like x to the power of something. I don't know if you all have learned that yet, but yeah. Then there are two parameters that we can adjust, which are known as C and D, which is a constant and the degree of freedom. And the second common kernel is the Rbf kernel, also known as the Gaussian kernel. So this uses like this exp here represents e to the power of something, and we can adjust this single parameter here called gamma, which is this y looking symbol. So I'll not be going into too much detail about these two kernels, but you can search them online yourself. And now we'll be going to the coding portion. Yeah, and you can see this meme here. Okay, so here I'll be using this very common data set called the iris dataset provided by scikit-learn, which is a Python library. So basically, this dataset consists data on 3 types of irises. The names are shown here. And then the data is on the sepal length, sepal width, petal length, and petal width, which are like these parts of the flower here as shown in the picture. And the data set also consists of targets, also known as like the classes, which classifies each of the data into the type of flower that they belong to. So 0 represents setosa, 1 represents versicolor, and 2 represents virginica. So firstly, we'll load the data by importing standard libraries like pandas and numpy. And then we load this function called load iris from sklearn datasets into this variable here called data. So now if we look at the data after loading it into the pandas data frame, actually this is not that important. It's just putting the data into a table so we can so that we can look at it better. We look at the first 5 samples of data and we see that yeah, this is just to get a few of the data. So we have these 4 columns: sepal length, sepal width, petal length, and petal width, and their class. So since these are the first few samples, all their classes are 0, which is the first type of flower. But for the purpose of this workshop, in order to visualize easier what is going on with the SVM, we'll only be taking the first 2 features, which are sepal length and sepal width. So if you look at the first 5 samples again, it only has these 2 features left, which are sepal length and sepal width. And now we'll be training the model. As Iwang mentioned earlier on, there's this very useful function, train test split for cross-validation, and we'll be using that on our X and Y data, where the X is like the data on the flowers, both the sepal length and sepal width, and the Y is the class of the flowers. And then this is the main part that we want to look at, which is from sklearn.svm import svc. So this svc will be the specific model that we are using, and is also known as support vector classifier, which is like a type of SVM that is used for classification. So here we'll be setting our model to this svc, and we'll be using the linear kernel for now, which you can try to change the kernels later on to see the different results. And then after that, we fit the model to the training data and get the accuracy of the model on the test data, which is 0.8, which is quite high, honestly. But because we only use if we use more features, it will probably be able to get a larger accuracy. And now we use Matplotlib to visualize the data. Using a scatter plot, we see that the data is as follows. It's quite hard to see here, but there are 3 classes: blue, red, and white. Especially the white class is, I think it's quite hard to see, but so in the scatter plot, we see that like based on the sepal length and sepal width, you can sort of clearly see that the blue points are near the upper right hand corner, red points are nearer to the right side, and white points are nearer to the bottom. But if you can see here, right, we see that there's some red points in between the white points. So you probably think that the SVM is not very likely to be able to achieve 100% accuracy because of the nature of the data. And using some Matplotlib functions here, namely this mesh grid and contour F. I'm not really sure what that means. But basically, it helps us to visualize the SVM and shows us the different boundaries. So just now we trained the SVM and it came out with the following boundaries, which separates the blue, red, and white data points pretty cleanly, I would say. Just that because of the data and the anomalies, some of the red points are in the white part and some of the white points are in the red part. So now I'll be sending the code to y'all, and y'all can try changing the code for the next, I would say, around 5 minutes. Yeah. Okay, yeah, once again, please post questions. And I hope you are refreshed after the break. And now I'll be consolidating everything we learned today before we end the workshop, which I'm sure most of you are looking forward to. So firstly, we learned about two main problems that can be solved using AI. The first of which is classification, which involves separating the data into two or more classes. The second one is regression, which involves using a function to map an input to a particular value, in other words, like a best fit line. Next, we covered different types of loss functions, including the 0-1 loss function, where wrong classifications add 1 to the loss, and correct classifications don't contribute to the loss. The L1 loss function, which takes the difference between the actual value and the predicted output to add to the loss. And finally, the L2 loss function, which squares this difference and penalizes the model for very incorrect predictions. Yeah. Next, we also talked about overfitting, where a model fits too closely to the data and doesn't generalize in order to get a very high training accuracy. As well as some ways to avoid overfitting, including regularization by penalizing more complex models, holdout cross-validation, which splits data into training and test sets, and finally k-fold cross-validation, which carries out holdout cross-validation k times on the data set. Next, Yikting talked about perceptron learning and the different activation functions, including the linear and logistic activation functions, as well as this perceptron on the right, which has the inputs, weights, activations, and outputs. We also explored that if we put many of these neurons together, it acts like a brain, in other words, a neural network. And the more layers we add, including hidden layers, the more complex the data will be, which may allow for it to fit more complex data, which is common in the real world. Finally, I talked about support vector machines or SVMs. We explored how they use support vectors to create the optimal hyperplane with the maximum distance away from the support vectors to classify the data. We found out that SVMs use the one versus all method to carry out multi-class classification, where it compares one class to the rest of the classes in order to create the boundaries. Finally, we found that SVMs can make use of kernels to transform the data in case the data is non-linearly separable. The common kernels include the Polynomial Kernel and the Rbf Kernel. And with that, we thank everyone for your attention and hope that you have picked up a thing or two from our Introduction to AI or Machine Learning workshop. Do check out the further workshop, Introduction to Deep Learning, if you would like to learn more. And now we'll be having the questions and answer segment where you all can post questions in the chat and we will answer them.